Okay, so the last talk is by Moni Naor. Moni is currently a professor at the Weizmann Institute. He received his PhD in 1989 from the University of California at Berkeley. And the interesting fact is that it was done under the supervision of Manuel Blum. He works in various fields of computer science, mainly the foundation of cryptography, and especially notable for creating non-malleable cryptography, visual cryptography with Adi Shamir, and suggesting various methods for verifying that users of computer systems are human. He was named an IACR fellow in 2008 for fundamental contributions to the scientific foundation of cryptography and for sustained educational leadership in cryptology. So this is what I found in Wikipedia.
Thank you. So thank you for the invitation and for the opportunity to speak in such a company. So I'll talk, as you heard, I'll talk about cryptography and data structures, match made in heaven. So cryptography is a very old subject, but it really started as an academic subject only in the mid-70s. Of course, the key papers of Diffie-Hellman and RSA. And what also started around that time, slightly earlier, is computational complexity theory, and there is a very tight relationship between the two areas. And the key idea of cryptography, you can say, is to use the intractability of some problems to your advantage, the bad news of one area or the good news of the other area, in order to construct secure systems. And based on that, on this theme, there's been great results. The areas of complexity and cryptography have really stimulated each other. And just to mention, the whole PCP started from a question of what happens when you want to get zero knowledge without when you want to have perfect zero knowledge without any computational assumptions. And key results in one area were applied in the other. And that led, I guess, Shafi Goldwasser, in your paper, which is already pretty old by now, her paper, an address that she gave to Fox in Fox 1997 to have the subtitle of Cryptography and Complexity, Match Made in Heaven. So in homage to this title, I'll talk about data structure. But before that, some news. Shafi Goldwasser and Sylvia Micali are the Turing Award winners of this year. It was just announced. Anyway, the thesis of this talk is that actually cryptography and data structures, the area of data structures, are quite related. And they have enjoyed a very fertile connection. Now, but unlike the the connection with complexity, which was usually celebrated, here somehow people hid it and did not celebrate the fact that, I'm using this and vice versa. And there are actually many examples, and what I'll do in this talk is give you some examples, which, of course, are a very biased sample of such developments. So let's start with the first example. It's not the first example that exists, but the first example I want to talk about, and that's Hellmans time-space trade-offs. So Hellman, another important development in the mid-70s in terms of cryptography, in addition to the invention of public key cryptography, was the introduction of the DES, the data encryption standard. Because there was something that the standard of encryption, of shared key encryption, that was considered good. And suddenly, this problem, well, not clear whether it was solved, but at least there was something to talk about. However, what was the problem? It had a very short key, 56 bits. Today, it's definitely very short, but even back then, it sounded like borderline. And Hellman, but still, to do a 56, if you want to do exhaustive search, was a pretty high number. So what Hellman pointed out is that actually you can do much better than spend 2 to the 56 all over again for each time you want to break DS. And he asked the question, suppose I have a function and I want to invert it, how costly it is. So if you're allowed pre-processing, so you're pre-processing and then you're looking at how the cost of any additional breaking. So if, for instance, if you build a table, a large inversion table, then of course it's a roughly order 1 to invert, depending how costly it is to access the table. But that requires a huge amount of storage. So we probably want to have less storage and are willing to work a little more. And so we have some sort of limited space, and then we're asking what is the best we can do in terms of time that we spend. So what Hellman showed in 1980 is if you want to invert a permutation, then you need storage S and time t times S, which is n. And if you want to invert functions, it's t times s squared equals n squared. So think of t and s being, let's say, n to the 2/3. And n here, capital N here is the size, is 2 to the little n. That is, capital N is the size of the universe, the number of the total number of keys that you can have. So how did he work? How did that work? So let's say we have a permutation. So we have a permutation pi. I'll only hint how you do it for a permutation. So you have a permutation pi. You can, let's, for simplicity, also think of it as one cyclic permutation. Doesn't really matter. So you can definitely go forward. That's the advantage that you have. You can go forward. So in order to invert the permutation, you can go all the way around. You can apply it to itself many, many times. So if, for instance, instead of being a cyclic permutation, it had only small cycles, it would be very easy to invert the permutation. So the hardest case seems to be when pi is a cyclic permutation. So what did he suggest? He suggested adding shortcuts. So you add every t steps, you add a shortcut. Okay. So the shortcut tells you if you get here to go back n minus t times, in order to, instead of going all this way, this will be a shortcut. So this means that when you're going forward, you only have to get to these special points, and then you can make a shortcut, and the time to invert would be, by going forward and using the shortcuts, the time to invert would only be t. So what you get is this sort of expression. And this is true for permutations. For functions, things are a bit more complex, and we have worse times. And actually, it's a very interesting open problem to try to improve these things. There are some lower bounds in some models. And these lower bounds, today there is a slightly different method, the rainbow table method, which is very popular. But these are still very, these things are probably the most important time memory trade-offs style. If you want to have online real-time style attacks on crypto systems, then probably you'll be using something of that nature. Okay, so this is Hellman's time-space trade-offs. What is the connection to data structures? So let's talk about the problem. Suppose that you have a bunch of books. That you have many books, and you want to arrange them on your shelf so that you'll be able to search under both under title and under author. So you don't have any. This is sort of an implicit. It's an implicit data structure. You don't have any other storage except the items themselves, and you can only access them using comparisons. You cannot. We're not talking about hashing at this point. Later on, we'll talk a lot about hashing. So you can only compare you can compare the author, see whether it's larger or smaller, and you can compare the title. So definitely the best you can hope for is order log n here. And the issue is, can you arrange, so of course, if you wanted just author, it would be very easy. If you wanted just title, it would be very easy. But the question is, can you do both? And in one of my first papers, while I was Manuel's graduate student with Fiat, Alex Schiffer, Jeanette Schmidt, and Ellen Siegel, we came up with an order log n solution. And I'm not going to show it, and actually it's true for many of the results. I'll just try to show the idea, the relationship between the crypto and the data structure. Anyway, so we came up with an idea. So first you split the records into k keys. If you have k, not just two, but you have k different types of keys, you split the records into k keys, into k sets. And what you want is that each set would be a nearly perfect sample for that key. So you split according to, let's say, title. Some of the books are considered title books. Some of the books are considered author books. And it's a very good sample. So if you know where the book is, if your book is not, the book you're looking for is not according to, was not chosen as part of the title book, according to the title set, you'll know where it should have been to within one or two locations. And you can do such a partitioning using Hall's theorem. Anyway, so now the problem is, of course, so you know roughly where it should be, but it's not sitting in the right place. So what you have among the other books, you have some sort of permutation of the original order. So you want to search in this permutation. Now you don't know things exactly, but that's okay. You can actually add a few bits and then show how to store them. So I'm not going to talk about all these things at all. I'll just mention that you still have the problem that you have a permutation, where the books went to. If your book was not in the thing you are looking for is not in the if you're looking for a book by title and the book that you're looking for is actually in the author section, so it's ordered in some according to some permutation of what it should be. And you can actually compute the permutation, you can compute the forward permutation, and you're trying to invert it. And what did we use? We used this sort of trick, whatever Hellman had, exactly the Hellman trick, except that T here should be constant, and we were able to store some small constant times n pointers, and then store them and then show how to encode them. So we could use exactly the idea of Hellman and come up with a solution which took only where each forward computation was each backward computation could be done in actually log time. So we could search for the book altogether in log time. So here we see an example, an idea that came up in the crypto literature, showed up in the data structure one. Okay, so let's move on and ask, so if we look back at Hellman's work, his analysis, the way he wrote it, assumed a lot of randomness on the function. The function that you were trying to invert, he assumed, was very random. And even if you take various projections of it, it still remains random. And it's better to work in a worst case style. I have a function f. Maybe I'm assuming some combinatorial properties that it's either a permutation or that it doesn't have too many, doesn't have a too high integer, things like that. But we don't want to assume that we're trying to invert a random function. Because it's not. It's a function related to ds. It's not a random function. So the question was whether you can come up with an analysis of Hellman's work without assuming anything about f. And with work with Amos Fiat, we had the idea of composing the function f with a k-wise independent function g. And of course, now if you want to invert f composed with g, it's right, you'll get from it something very similar to inverting f. I mean, in terms of if you can invert f composed with g, you'll also be able to invert f. And the problem is that k, now each time to evaluate the function, you also have to evaluate g. Now, K, what should K be? K should be roughly, I mean, I didn't show you the actual Hellman construction, but K is going to be pretty large. It's going to be something like capital N to the 1/3. So it's going to be a very large value. And we want to, so each time we have to spend, if you look at the sort of traditional construction of K-wise independence using polynomials or whatever, then that's very expensive. Then each time you want to evaluate the function, you have to invest time into the 1/3. So we're faced with this problem, and I'm not going to tell you how we solved it back then, but actually today there is, I will hint of how you can solve it today. Today, with relationship to data structures, there are actually solutions of K-wise independent functions that can be evaluated very quickly in order 1. Okay. So, so let's switch to the dynamic dictionary to hashing problems. So we want to come up with a data structure for representing a set of words S from a universe U, and oops, what's happening here? The sign, I guess the red. You don't see red or something. Anyway, so the size of the set S will denote with little n, and the size of the universe is little u. And we want to be able to do lookup, insert, and delete. And the performance we consider lookup time, update time, and the space, the amount of space we need. So we want actually constant time operations and minimal space consumption. And this is, of course, a very problem that's been investigated for many years. I guess the first interesting analysis is of linear probing by Knuth. But still the trade-offs are not fully understood. So I guess this is Knuth from that time, from the time he wrote it, which I think in Holmes had you mentioned the Knuth from 66, but you had a picture of him from much later, and I think this is closer to it. Anyway, so in work with my students Yuri Arbitman and Gil Segev, we came up with a solution that for any polynomial number of sequence of lookup, insert, and delete, all operations take constant time, and the probability is over the initial randomness, and then this statement is true, that all operations take constant time, some fixed constant, with some probability 1 minus 1 over poly. So again, I'm not going to show you the whole thing. I'm going to show you a few ideas which are related to crypto. So first you may ask, why are we so interested in worst case and not amortized or whatever? So first, if you have some sort of, you're using it in the hardware type environment, it may be very important because you're building it. You don't want to waste too much. You don't want to waste the amount of hardware you need to invest is connected to the worst case, so you don't want that. Another reason is comes actually from cryptography. Suppose somebody is trying to perform a timing attack on you. So you have clocked adversaries. They look how long it takes you to respond and act accordingly. So they can learn your internal randomness. Okay, so they can actually learn your internal randomness and reconstruct the hash function from seeing which operations take a long time and which operations take little time. And therefore, they can find bad inputs. So if you're in any sort of adversarial environment, it's bad to use such hash functions. And in general, even if it's a more benign environment, if it's somehow inside an operating system and according to the time it takes to perform the operations, the next operation is affected, something like that, then you're losing the fact that the assumption that the adversary is oblivious to your randomness. So we want to have worst case type things. All operations take exactly the same amount of time. Okay, so in terms of space, we may want now to have really the minimal amount of space. So you want, if you're storing n elements out of a universe of size u, oops, Now you don't see it all the universe. So here there's some universe, which I guess you can't see. So there is a universe of size u. You have a set of size n. If you're actually storing each element explicitly, it takes you n log u bits. But we need less than that. We need just log u choose n bits to represent a set of size n out of u. So you're wasting roughly n log n bits. And when u is small, when u is a small polynomial of n, then this may be significant. And for instance, if you're doing Bloom filters, so Bloom filter, not the Blum filters, if you're doing a Blum filter, so you want to solve the approximate set membership problem, and so you have a subset, again, same type of subset, you don't see the universe due to coloring problems. So you want to say yes on elements in the set, you want to say no on elements not in the set, but you're willing to suffer some error of gamma if it's not in the set. And here you can show if gamma is a subconstant, that the amount of space you need is n log 1 over gamma. We don't know exactly for the dynamic case, we don't know exactly when the set can change dynamically, we don't know exactly how it behaves when gamma is a constant, but certainly when gamma is subconstant, then this becomes the significant term, n log 1 over gamma. So this is the famous Bloom data structure from 1970 solves this problem to a certain extent. But we can actually use dictionaries to solve it and get a slightly better solution. At least again, when the case for gamma, which is constant, simply by hashing to a small set, hashing to a set of size n over gamma. Okay, so you started from universe u, you hash it to a set of size n over gamma, and to insert x, you need to store g of x. Instead of storing x, you store g of x. And in order to check whether it's in, you check whether g of x is in the dictionary. So now the problem that you have is your new universe is of size n over gamma. And you don't have enough bits to represent each element separately. That would be very wasteful. You will be getting something which is, you wouldn't be getting such an expression. On the other hand, if you have an optimal solution, optimal in terms of memory to the dictionary problem, then you would have an expression like n log 1 over gamma. So just for comparison with the original Bloom filter, that will be times log, times another constant times log 1 over e, log e. So what's the source of waste? How can you waste space in a hash table? One is if it's not full. The table is not full, the empty entries are really wasted. I'm not going to describe how we solve that problem. The other is you're using too much in order to represent an element. It's really, you're using to represent an element log u bits, but really there is already, if I'm searching for an element in location I, there's a lot of information in the fact that I'm in location I. It means that somehow the element led me to location I. So you don't really need to store all of these things, okay? And we're going to use this idea. We're going to use the idea that we can get rid of some of the space. So I think for some of you will understand the analogy. If I'm standing and the fridge is open, it means that I'm hungry. So I don't need to remember that I'm hungry, right? I can throw away this bit that I'm hungry. So this is the same thing. If I'm looking at location, we'll be using our hash functions will be a permutation, and we'll be using pi of x as the new identity of x. And the prefix of the new name is going to be the identity of the cell of where we're going to search for it. Okay, so when the cell is being probed, we know the prefix. There isn't any point in remembering it. So essentially, so if we're storing elements in bins, and let's say then we're searching inside the bins, it's the second level, then really there isn't any point in storing all of this information inside the bin. Instead, we can get rid of the part that tells us that this is led us to 1, to 2, to 3, etc. So we can store less information. So let me talk about cuckoo hashing, because that will be important both for this and for the next application. So cuckoo hashing is a wonderful scheme. If you don't know it, you definitely should. I think it's one of the great inventions in computer science of the century. It was suggested by Pine Rodler in 2001. And it's extremely simple. What they're suggesting is you have two tables, T1 and T2, each of size roughly larger than n. And you have two hash functions, H1 and H2. In order to do lookup, you have to look up in T1 and you have to look up in T2. So you compute H1 of, to search for X, what you do is you compute H1 of X and look up in T1. You compute H2 of X and you look up in T2 to see whether it's here or whether it's here. These are the only two possible locations where X can be. Okay, so lookup is extremely simple, two hash computations and two lookups. And the nice trick is that insertion is also pretty simple, and hence the name Cuckoo. It comes from the cuckoo bird that kicks away the eggs of other birds. I suppose North Americans need this explanation because it only happens in Europe and this area, not in North America. The cuckoo birds don't behave like that. So that's perhaps why Pine Rodler were from Denmark. Anyway, still are. So in order to you put X in location H1 of X. If it's empty, great. If it wasn't empty, you need to find a place for the guy that was there, Y, and you insert it into the other table, and again you kick out whoever was there, etc. So just do a simple example. You're trying to insert E. You go to H1 of E is equal to H1 of A, so you kick out A. A goes to H2, to its H2 of A. Y was there. We need to find a place for Y. H1 of Y was empty, so you put it there. And that's it. The thing finishes. So this is very simple, though. Of course, the question is, why does it work? And it doesn't always work, but it works with reasonably high probability. And it works, if you look at the Cuckoo graph, then you have a set S defining the set S. You have here you have a bipartite graph. Each location here corresponds to the locations in the memory. The nodes corresponds to locations of the memory. The edges correspond to elements, and you have an edge connecting. For each element X, you have an edge H1 of X connect H2 of X. And now the nice thing is that the S is successfully stored if and only if every connected component in the Cuckoo graph has at most one cycle. Okay, and the insertion algorithm achieves this. So, this is pretty good, except that you're wasting a little, right? You need a little more than twice as many elements. So roughly half for this thing to work, roughly half the locations will need to be empty. So there are various ways of getting it to be denser and denser. And in particular, in our work, we showed how you can actually work in bins and get provable results. But the point is that that's not enough in order to get 1 plus little o of 1 of the information theoretic bound. we need to get to use these permutations that I mentioned. So in particular, right, as I said, you use a permutation and you partition it into two parts. You look at the bits as partitioned in two parts. The first part tells you to what bin it should go. Okay, the left part tells you to what bin it should go. And the second part is sort of the new identity. We'll encode the new identity of the elements. If it's going to be in a certain bin, there isn't any point in storing it. So if we know that it's going to be in this bin, and the bin corresponding to it, we can throw away this part and store just this value. Okay? So we just store this value and can get rid of the other one. So how do we get permutations? So here we use again crypto. We look at the construction of a Feistel permutation that is in the construction of DES used Feistel permutation. The construction of Luby-Rakov of pseudorandom permutations use the Feistel permutation. And essentially, what we have here is we partition into left part and right part. We apply a function here which should be pretty random. We know how to construct. Remember, our problem is we have good constructions of k-ways independent functions, but we don't have great constructions of k-ways independent permutations. So what we do, let's say, is in each step, or this we can do. This is it's a little bit more involved, but let's think of it as just one step here. So we apply a k-ways independent function, XOR it with a left part, and this tells us the bin number, and R can remain unchanged as the new ID. This is, and what we have here is some sort of highly independent hash function, but not too high, so that we can still represent it in sublinear space. And so how do we get something that is close to a k-ways independent permutation? So we do this we do it here. We can get pi 1 and pi 2 can be just pairwise independent permutations. But here inside these two permutations are constructed exactly as I showed before. Okay, and each one of these functions, f1 and f2, are going to be highly independent, but they're functions, not permutations. The whole thing, the whole result is a permutation, and we can get a collection of delta dependent permutation, where delta is something like k squared over square root of u, and you can compose a few of them and reduce the error. So here we've used the basic idea of crypto of constructing pseudorandom permutations in order to come up with the analog of k-ways independent permutation that we need. We still don't know how to construct. So we still need. So this is both in the work that I told you on making Hellman's result rigorous, and here we still need the ability to come up with k-wise independent functions which can be evaluated in order 1 and have reasonably succinct representation. So so let's go to our final application, and also the construction that I still owe you, and that's hashing for domain extension. So suppose that we have a pseudorandom function that operates on a fixed domain size. So let's say it operates on n bits. So it's from n bits to n bits, and it's like a pseudorandom permutation. So we want to construct a pseudorandom function on any domain size, from m bits to n bits. So we have one on fixed that maps n bits to n bits, and we want to map m bits to n bits. So what can we do? And we measure such construction by the domain, how large the new domain is, the security as a pseudorandom functions in general, when, oops, what's happening? Okay, in general, we measure security of a pseudorandom function by the number of queries it can answer, the time the attacker can attack it, and epsilon, the distinguishing probability. So we have a construction with kt and epsilon, and we want to come up with a construction with k prime, t prime, epsilon prime, which are as good as possible. Okay? So we measure the construction by by the deterioration of the security, how worse are k prime, t prime, and epsilon prime are, how worse they are compared to k, t, and epsilon, and the number of calls made to the underlying pseudorandom function. So even if you look at the original Goldreich, Goldwasser, Mikali paper on pseudorandom functions, constructions of pseudorandom functions, you can apply it and get such a reduction, but it wouldn't be so good in terms of the number of calls to the function. It wouldn't be a constant number of calls to the underlying pseudorandom function. So what can we do? Luckily, Levin had the idea, and I think it's already in the original paper, in the original GGM, or maybe it's an on paper, but actually it's explicitly described in one of Levin's paper, much more so than many other ideas that are only hinted. Anyway, so what you do is in order to extend the domain, you use pairwise independent hashing on the new large domain, and you hash it to the original domain. What's the problem? The problem is birthday. So if you have q queries after something like q, you cannot use it for more than q squared over 2 to the n applications, because after after this many, the probability of a collision is q squared over 2 to the n. So the deterioration in terms of distinguishability is q squared over 2 to the n. And the question is whether, so it's a very good construction in terms of the number of applications, right? We're applying just one hash function which is pairwise, so that could be very efficient. And then we're applying the original pseudorandom function, so that's great in these terms. But in terms of security deterioration, it doesn't work, and you cannot apply it you cannot do more than square root of 2 to the n many queries. So, okay. So what so there have been various constructions trying to achieve it, and in recent work with Itai Berman, Yiftach Heitner, and Ilan Komarbodsky, we came up with a construction that needed to call the original function, the underlying function, 2 times, and this is of course reversed, right? Security number of calls is reversed, right? This is the number of calls and this is the security. Anyway, and this also appears here suddenly. Strange things are happening. Anyway, and I can't even blame the fact that it's not my computer in this case. I guess it's my own doing. Anyway, so what happens in terms of security, we can get the security. This should be here. We can make the security, the deterioration in security, to be as small as we wish. We can have 2 calls and other work, 2 calls to the underlying pseudorandom function plus other work, and the security can be of the form q over 2 to the n, but it can be even smaller if you're willing to spend more work, but not cryptographic work. So how did we get it? We did it by using other people's work, the best type of result. You let other people do the work, and then you just snatch it and apply it. So the people who did the work were Pa and Pa. I guess Blum and Blum are not the only ones who work together. And they came up with a construction of highly independent functions that can be easily evaluated in the spirit of cuckoo hashing. So you need a hash. Well, you need their point was this is their construction. So you have functions f1 and f2, which are going to be essentially f1 and f2 are going to be, think of f1 and f2 as truly random functions. But where can you have truly random function? If you have a table, if it's just a table lookup. So their domain is limited. So, so we will be applying h1. h1 is going to be something like log n or log or in our notation here, n-wise independent. h2 is also going to be something like n-wise independent. Remember, n is the original number of bits. We're going to apply, h1 is going to map to a relatively small, f1 maps to whatever independence we want. So we're going to apply, so in order to evaluate our hash function, you have to apply, you have to compute h1 of x, you have to compute h2 of x, then apply f1 to them, apply f2 to them, XOR the result. And then the whole thing would be XORed with another something like n-wise independent function. So n is the number of bits. When I say n, I mean the number of bits, or in whatever application, whether in your, sorry. It makes sense to talk about n when we're talking about the crypto application, and if we're talking about the data structure application, we'll talk about log n. So log n is still pretty high, but we can deal with that as well. I'm not going to tell you how. So this is another way, this is a pictorial way of viewing it again. You have a large domain, you apply the hash function, you get a small domain, you apply f from here, you XOR the two results, plus you're using another G for sort of those that didn't make it. And what they showed, what FindPath showed, was they showed this type of result. If the H and G, these functions, these families, if these families are k-wise independent, and f is truly independent, then the resulting family that we get is k over 2 to the k indistinguishable from random by any k-query non-adaptive distinguisher. Okay, so non-adaptive distinguisher. So it's not quite what we want. We want, if we're trying to use it for whatever application, both in the hashing, both in the data structure application and in the domain extension application, the adversary can be adaptive. I mean, certainly if you think of adversaries in the context of pseudo-random functions, they are adaptive. We think of them as adaptive. So luckily, the way the proof is written, you can easily get from it a stronger result. And you can actually show that it holds for adaptive distinguishers as well. And again, you can use their work and get there exists quite general statement that tells us that if you prove it in a certain combinatorial way, we will be able to translate it and obtain a result that is good against adaptive adversaries as well. So the way the domain extension would look like is something like what we saw before. We will we'll use, f would be the original pseudorandom, the underlying pseudorandom function. We'll have g and h which are k-wise independent. And the result would be, we don't lose anything in Q. We lose a little in the time because we still need to evaluate the hash function. And in terms of the deterioration in the epsilon, we get an expression of the form k over 2 to the omega k, q over 2 to the k. So once k is larger than log q, we started getting reasonable results, and we can. And this is what I told you before. We can make it as small as we wish. Okay, so this is it. These are roughly the examples I wanted to show, and I would end up with just one question. Is there a general theory that explains these tight relationships? How come we're getting so many, we're able to go back and forth between crypto and data structures so easily? Is there just a general explanation for this phenomenon? Thank you.
What is the equation behind G function G?
G takes care, the probability isn't small, the probability of failure is something like 1 over the table size. G takes care of failures, makes the probability much, much smaller.
There are those real-time dictionaries of Martin Ditzfeld-Binger. How do they relate?
Oh, okay, Ditzfeld-Binger, you are talking about, okay, Ditzfeld-Binger got rid of, I told you there is still the original Ditzfeld-Binger-Wolfel. You're talking about that?
Oh, the real-time Ditzfeld-Binger, real-time dictionary.
Okay, no, you're talking about a very old papers.
Very old.
Okay, no, they're not space optimal. But no, but some of the work here, Ditzfeld-Binger and Wolfel have, they extended the pi and pi result to get rid of, I told you can get rid of the fact that you have log n independence. You can actually get it to order 1 independence. You never have to work more than order 1. So that's actually it follows from the work of Ditzfeld-Binger and Wolfel.